Hello everyone, thanks for organizing this workshop. It's my pleasure to join here. So my name is Bin Jianye, and this paper is supervised by Professor Yulong Ding from University of Birmingham, and also there are some other co-authors from our industrial partner, the CRC chain. So today, my title is Experimental Performance of Physician Material-Based Real Container for Cold Chain Transportation. So firstly, I would like to briefly introduce the background of this paper. So currently, as you know, the refrigeration of the cold chain relies on diesel power. This kind of technology is efficient and also highly polluting. Also, there's a risk of the high operation cost. And also, when the compressor failure occurs, there will be a total waste of the atom inside. So to cope with these issues, we introduced a technology called the Pista, the fission material-based cold energy storage. So the principle of this technology is simple. When material changes from liquid to solid, we define it as the charging process. In this process, the material will absorb cold from the ambient, and when the material changes from solid to liquid, it can release cold. So in this way, it can provide cooling. So there are some basic criteria to select suitable materials. So such as high energy storage density, a low supercooling, and high thermal conductivity. So these are for the charging performance. So if your material have a lower supercooling and higher thermal conductivity, it means the charging process will be faster. In this way, you can save time and save some energy. And also, we expect the material to have a suitable viscosity. It means that it can reduce the risk of leakage. And of course, the cost should be low and should be food safety. Also, we hope the material can have a long cycle life up to 10 years, which is similar to the mechanical unit. So based on this concept, we design the TCS plate, the thermal energy storage plate, to include the material inside. And also, we install up to 10 plates inside the current 54 feet shipping container. So you can see from the second figure, there are 9 plates on the ceiling and 1 on the side wall. So for each plate, it can include up to 120 kilos of materials. So for each container, there will be a total of 1.2 tons of material inside. And from the third figure, you can see the blue one is the charging facility. It's a mechanical unit, but it's powered by electricity. So once charged, there will be no actual energy supply to provide cooling. So in this way, the container can be transported by the normal trucks and normal trains, and also it can be transported flexibly between the different transport modes. So in this paper, we also introduced some performance index, such as charging rate, charging efficiency, and system COP, to evaluate the performance. Also, we want to compare the energy and cost and emission performance of such a container with the traditional ones. So for the materials, based on our previous CFD simulation, we got to know a material with a melting temperature at around 5 degrees suitable for such an application. So here we use the materials with a melting point at around 4.96 in the container, and the material have a latent heat at around 180 kilojoules per gram. Thermal conductivity not quite high, it's 0.2. So firstly, we do the charging experiments. So for the charging, the ambient temperature you can see from the top line is around 35 or 36 degree. And the dashed line means the material temperature. So when the material temperature decreases below 5 degree, it means that the materials are fully charged. So you can see it needs around 5.5 hours to fully charge the materials. So here I want to say the charging time depends on the cooling capacity of the refrigeration unit. If you use a higher refrigeration unit, the charging time can be shortened. For the discharging performance, for the cooling performance, we did three kinds of experiments. So first, they're under static conditions, and the second is under the dynamic conditions, for the road test. And the third one is the road test as well, but carrying the real atoms inside. So firstly, you can see the result in this slide, showing showing the results of the discharging process under a static condition. So for the top line is also the ambient temperature. You can see during the day and night, the temperature changes quite a lot. The highest can reach up to 40 degrees, and the lowest can decrease to around 20 degrees. However, if you see the temperature inside the plate and also the temperature inside the container, the second one, the dark blue one, the temperature keeps really stable. It's around 8 degree and below 10 degree. The temperature range is really suitable for fresh atoms. Because normally the fresh atoms require temperature between 2 and 10 degrees. And also for the under the dynamic conditions, for the road test. So for the first two figures, it means the temperature inside. So here we also want to know the temperature distribution inside the container, because unlike the current ones, we do not have any forced air inside, because there will be no electricity with the container. So there will be no fan, no forced air. So in this way, we worry about if the temperature will be uniform or not. So here we use different thermocouples at different locations to record the temperature inside the container. So the green line means the ambient temperature. You can see it still fluctuates quite a lot. But if you see the temperature from at different points, you can see you cannot see obvious difference between them. It means that the temperature inside the container is quite uniform, so even without any forced air. And for the below two figures means shows the humidity. Because humidity is not the important index for the cold chain applications. So you can see the green line is also the ambient relative humidity, and the other curves showing the relative humidity at different points. And most of them located between 80% to and 90%. So from the literature, we got to know the most suitable range is around 85% and 19%. So the relative humidity range is also suitable for such for the. And finally, we did the experiments also under the dynamic conditions, but carrying real atoms. We're carrying 4 kinds of green leaves and fruits inside. So the container was transported by a normal truck between Chinese cities. So the green line, from the left figure, green line also means the ambient temperature, and the other curves means the temperature inside the container. So you still can see the temperature inside is quite stabilized, and it's between 5 to 10 degrees. It's located in the required temperature range. And the right one shows the humidity. Also, the humidity is around 80% and 90% is also located in the suitable range. So this slide shows the temperature and relative humidity of the carrying atoms under the dynamic conditions. So from the left one, we still can see the atom's temperature is also quite stable, and the humidity is close to 100%. This is interesting because this means that there will be no water loss during the process. So for the current ones, maybe someone noticed that some drivers will spray water during the transportation process because using the forced air. The big issue is that there will be a heavy water loss during the transportation process. And in this slide, we show the comparison of the energy and the cost of the TS-based, the thermal energy storage-based container with the diesel-powered container. So for our real operation, for delivery distance at around 2,300 kilometers, we can see the power consumption for the diesel one and also for the electricity one. And also we use the normal diesel price and electricity price. So in this way, got to know the operation cost can be reduced by up to 85%. And here I also want to say, if we consider the renewable energy and also the electricity policy, such as the peak price and off-peak price, the operation cost can be further decreased. So we collaborated with the National Agriculture Product Center, so carrying 4 items such as green leaves and also strawberry mango. So they from their report we can see they give the 4 index: the hardness, color, pH, and the solid content. So if we compare the data before and after the transportation, we can see there's no obvious difference. It means that this kind of technology is reliable for transport the fresh. So finally, I give some conclusions. Here I want to mention there's some conclusion from our latest experiments, not included in this paper. So for system COP during the changing process was found to be 1.84. So for currently diesel ones, the COP cannot reach higher than 1.5. So system COP will be higher for such a technology. And also once charged in 2 hours, the container can provide 2 to 8 degree cooling for up to 96 hours. It's around 2,000 kilometers. And the emission can be reduced by 70% when using the PCM-based container, and also the flexible transport between different transport modes without extra energy supply when once charged. Also reduce water loss compared with the forced air, and the important that there's no condensed water drop. It's very important for carrying items with packages. And also introduce the advanced information technology. It can provide the real-time monitor of locations, temperature and humidity, the door opening, and also the important the availability of the cold energy, so they can tell the driver and tell the customer so how many miles you can still drive, you can be left. And also the mobile and fixed charging facility with the information technology can provide real-time location and availability information. So it's also for the quite flexible for the driver to choose the optimized route, and also it's easy for them to find the most convenient charging site. So that's all my presentation today. So if you have more questions, we can discuss later. And also if you have questions, you can contact me. Thank you.